I would like to introduce you to Yarin. He's coming from the University of Oxford, and he will have now a session on Bayesian deep learning. So please welcome him.
Okay, we got that working. So can everyone hear me? Is that okay? Is the mic okay? A bit higher, okay. I don't think it's going to go a bit high. Okay, we can use that one maybe. Is that better? Does that make any difference? What if I shout? Is that better? Okay, I'm going to shout. So, thank you very much for coming to the talk. I'm going to start with a simple question. Who thinks autonomous cars are cool? Who likes autonomous cars? Okay, who thinks probability theory is cool? Okay, so a lot of my talk is going to be autonomous cars and probability theory. If you didn't raise your hand, we're going to have some other stuff as well. Yeah, so I'm Yarin. I'm an associate professor of machine learning at the University of Oxford. We're going to talk today about Bayesian deep learning. If you don't know what Bayesian deep learning is, I'm going to explain what that is very soon. Today we're going to give a brief introduction. We're going to talk about the language of uncertainty. We're going to talk about Bayesian probabilistic modeling and about modeling of functions. And let's start with a quick introduction. So over the past few years, we've had many advances in machine learning. And if you actually look at the history of the field from the past, like 10 years ago, 20 years ago, you actually see how machine learning has changed very much from just being applied to toy problems, to toy tasks, to actually being deployed in real-life scenarios, in real-life settings. And slowly but surely, we're heading over control to these automated systems. Sometimes even in situations which become life-threatening to humans. For example, in the medical domain, we have automated decision-making or recommendation systems trying to diagnose whether you have cancer or not. In automotive, we have autonomous control of drones or self-driving cars. In high-frequency trading, it's been going on for a few years now. We've been giving these automated systems the ability to affect economic markets on global scales. And all of these can be quite dangerous. So let's look at a concrete example. So in medical diagnostics, diabetes is an exciting new startup which doesn't really exist yet. I have a feeling that by the end of the talk, someone's going to start that. Claims to automatically diagnose diabetic retinopathy, which is basically a type of diabetes that you can diagnose from these pictures of the blood vessels in your eye. So this is a picture of the blood vessels that you can take by just taking a picture of the eyeball, and you can basically diagnose whether basically that's what physicians use to diagnose whether you have diabetic retinopathy or not. So yeah, this startup claims to automatically diagnose diabetic retinopathy. They get 99% accuracy on their 4 train test patients. And the engineer has trained 2 deep learning models to predict the probability Y of diabetes, given some input fundus image X. So probability Y given input X. Now, the engineer trained 2 systems, and they run the system on your fundus image X star, which is the thing over here. We have some system F1, some system F2. Now, which system would you want the engineer to use for your diagnosis? Show of hands, who wants model F1 to be used for the diagnosis? Who wants model F2 to be used for the diagnosis? Okay. Everyone is correct. You want none of these. You want the system to say, I have no idea what's going on. I'm going to refuse to diagnose you. I'm not going to say that you have diabetes or you don't have diabetes. It's very far away from the data that I've seen before. Another example is in autonomous driving. Autonomous systems are very diverse. We range from simple robotic vacuums to self-driving cars. they're largely divided into systems which are either control behavior with a rule-based system or learn and adapt to the environment. Both can use machine learning tools. For example, we might use machine learning for the low-level feature extraction, perception, or we might use reinforcement learning for the decision-making. A real-world example would be assisted driving. So assisted driving is a system that uses machine learning to decide whether to brake or accelerate or like steer left or steer right to follow a lane, or if the car ahead of you is stopping and so on. We actually had the first fatality of assisted driving back in 2016, in June 2016, when a low-level system failed to distinguish the white side of a trailer from bright sky. This is the press release from Tesla. Neither the autopilot nor the driver noticed the white side of a tractor trailer against the bright sky, and so the brakes was not applied. And then we had another fatality a year after, and then we had another fatality the year after. If the system had identified its own uncertainty, perhaps it could have been able to alert the user to take control over the steering, or propagate its uncertainty to the decision-making. Basically, in medical applications, in robotics, in sciences, in lots of other places we end up using machine learning. We can't use machine learning models that give us a single point estimate, single value in their prediction. We must use machine learning models that answer 10, but I'm not uncertain, or 10 plus minus 5. Basically, I want you to give me a distribution over the possible predictions, so the possible outcomes. Can dive a bit deeper into autonomous driving. Told you we're going to have a lot of autonomous cars in this talk. And the machine learning pipeline that we actually use in self-driving cars follows roughly, starts with a processing of the raw sensor input, for example, with perception models, for example, with image segmentation to find where the other cars and pedestrians are. This output is then fed into the prediction model, where for example, we need to decide where the other car would go, where the pedestrian would go. And the output from that is fed into some higher level decision-making procedure. Example, a rule-based system, if there's a cyclist next to you, do not steer to that side. Industry is actually starting to use uncertainty for a lot of these components in the self-driving car pipeline. For example, we use pedestrian prediction models to predict the distribution over where pedestrians will be in 10 time steps, in 20 time steps. Or we use uncertainty in the prediction components. So this is one of the large startups in the UK working on autonomous driving, publishing a paper on efficient computation of collision probabilities in safe motion planning. Or this is by Toyota, publishing a paper on uncertainty-aware driver trajectory prediction in urban intersections. These things are basically using tools that we're going to talk about in the next lecture and in the lecture tomorrow as well. So above are different examples of uncertainty. There are many other sources of uncertainty. For example, test data might be very dissimilar to the training data that we saw before. This is the example over here. This is the training data that we saw, and this is a new test point that he gave me. In model trained on diabetes photo, a photo of diabetes fundus from subpopulation A, which is over here. It never saw subpopulation B, which is U over here. Then in that case, we would say that the images are outside of the data distribution that model was trained on. The desired behavior would be to return a prediction, attempting to extrapolate, but also saying the information, additional information saying the image lies outside of the data distribution. So the model over here was trained. By the way, if the model was also trained with subpopulation B, if you give me some label over here, then that should decrease that uncertainty for these points. Another example is uncertainty in the model parameters that best explain the data. So we can have a large number of possible models that can explain the data. So over here we have some data points, X, Y pairs, and we have 4 different models that basically go through the data, explain the data. But over here we have a gap. We don't have any data, and we don't really know which one is the best model to explain the data over here. Over here we have high uncertainty, which model parameters to choose to predict with. And this affects how we predict with a new test point. Another example is we might have noisy labels. For example, we might have measurement imprecision from a sensor, from even a CCD sensor from a from a camera. We might have expert mistakes in labeling the data or crowdsourced labels, which are very noisy. In that case, even if you have infinite amount of data, the ambiguity inherent in the data itself is always going to persist, is always going to stay there. Deep learning models do not capture many of these different types of uncertainty that we talked about. Regression models would often output a single scalar or vector. Classification models would output a probability vector, which often is interpreted incorrectly as model uncertainty. So if this is the training data over here, and this is the output from the classification model, and this is your test image over here, then the model would say confidently, oh, you definitely have diabetes over here. This is like the possible uncertainty that it could have if it were to capture uncertainty. When we combine probability theory with these deep learning models, then we can capture uncertainty in a principled way. And this is a field known as Bayesian deep learning. This is a picture from the first Bayesian deep learning workshop we had at NIPS, 2016, I think, I don't remember. Bayesian deep learning has become it's actually a very old field that has been around for a long period, like a long, long time, and we're going to talk about the history of the field later. But in recent years, we had a boom in research, and there's lots and lots of exciting stuff going on in the field. I'm going to give you a taste of what's going on in the field today and tomorrow. Just to give you an idea of how big the field has become, this is the workshop, the Bayesian deep learning workshop at NIPS has been the second largest workshop of the conference every year for the past 3 years. I think we had more than 2,000 participants in that workshop from 3 years ago. I'll give you a concrete example for what this uncertainty looks like. So this is an example picture from a dash cam sitting in a car, driving through the streets in some part in the UK. If you want to use that to do autonomous driving, to do self-driving, then you would want to get an output that looks like this, basically semantic classes for each pixel, telling you whether that pixel belongs to, is it part of the street? So this pixel is part of the street, sidewalk, sign, building, and so on. Your deep learning system, your perception system might give you this output. Now this is quite bad because that means that your autonomous car, self-driving car, is going to take a hard left into the traffic sign over here, into the traffic light. However, if you actually visualize model uncertainty, then you can see that model has no idea what's going on in that part of the space. And then you can use that information to slow down, collect more information, alert the driver to take control, and so on. I'm going to give you another teaser, which is actually how do we get these uncertainty estimates? Who knows TensorFlow? Just show of hands. Okay, that's very good. So this is just a normal TensorFlow model where we start from import some layers and then define input layer, dense, dropout, output layer, and then we define, compile the model, then model fit on some X train and Y train, some data. And then we do the following 3 lines of code. We do model.predict on X test 100 times with dropout turned on at test time, collect basically a Python array of samples. Then we take numpy.min, numpy.variance, and just plot these mean and variance. That's all. This is actually working code. You can go on bdl101.ml/play. You can play with this code to try to break that, to see what happens. You can do that now, you can do that later. which leads me to, if you actually go on bdl101.ml, then you can actually find all the resources for this talk and for the talk tomorrow as well, including the demos and some recaps and some notation and some other fun stuff. Today, we're going to talk about, we're going to try to understand why this piece of code that we just saw makes sense. Today and tomorrow, basically, we're going to try to formalize the foundations of why the stuff that we talked about makes sense. We're going to talk about the formal language of uncertainty. We're going to look at tools to use this model, to use this language in machine learning, known as Bayesian probabilistic modeling. We're going to look at techniques to scale these things up to real-world deep learning systems like modern variational inference, and develop big deep learning systems which convey uncertainty with real-world examples. As a side note, we're going to have basic concepts marked with green in the top left over here. Basically, if you just want to use these tools for applications, advanced topics will be marked with amber if you want to develop new stuff in Bayesian deep learning by yourself. I will most likely go for the more advanced stuff quicker, and then you can just go over the derivations slower at your own pace later on. So let's start with Bayesian probability theory, the language of uncertainty. Basically, we're going to see how we can derive the laws of probability theory from rational degrees of belief. So this is a small piece of Python code defining a function called toss that probability 0.5 will print heads, otherwise tails. We're going to define something called a unit wager, which is a promise note where the seller commits to paying the note owner £1 or euro if the outcome of the toss is heads. Otherwise, they're not going to have to pay anything. This is a tradable note, so you can sell it to someone else. You can do whatever you want with that. You can go and claim that whenever you want. This is an actual example of a wager from 1845 from New Zealand for an amount of 3 pennies. So we're going to look at a concrete example, an actual betting game to try to formalize some of these ideas and develop some philosophical arguments about what does probability mean. For that, I need a volunteer from the audience. Who wants to volunteer? Okay, we have a volunteer. Would you pay 1 penny for a unit wager on heads, i.e., give me 1 penny to buy a note where I commit to paying you £1 if the outcome is heads? I'm asking you. Would you give me 1 penny for this unit wager? Oh, you wouldn't? Okay. Who in the audience would pay 1 penny for this unit wager? Okay, who would not? Okay. Okay, that's fine. Who in the audience would pay 99 pennies for this unit wager? Okay. Who would not pay 99 pennies for this unit wager? Okay. Who would pay 5 pennies for this, just out of interest? Who would pay 20 pennies? Okay. 95 pennies? 60 pennies? Would you sell a unit wager for p pennies on heads? Basically, I'm going to give you p pennies for the note, and you have to give me £1 if the outcome is heads. Would you sell unit wager for 5 pennies? Who would sell a unit wager for 5 pennies? I give you 5 pennies and you have to give me £1 if the outcome is heads. Who would sell a unit wager for 95 pennies? So you probably see the symmetry over here. I'm going to ask a more difficult question. What if you have to set the price, P, and commit to either sell the unit wager at P for heads or buy one, and I will decide whether to sell you the note or to buy from you. So basically, I sell you, you have to give me the P pennies that you decided to buy. So I sell you, then you have to give me P pennies to buy the note, where I commit to paying you £1, outcome is heads. I buy, then you get P pennies for the note and have to pay me £1 if heads. So who would set P equals 0.05? Would anyone set P to be 0.95? What about 0.2? 0.8? 0.6? 0.5? Okay. I have a feeling that some people yeah. So this is, think about it later. Basically, what P would you set if you're forced basically to choose a P? Basically, I stand with a gun to your head and you have to choose a P. You have to choose a probability P for this event. So a person with degree of belief P in event A is assumed to be willing to pay anything up to P for unit wager on A, and willing to sell such a wager for any price above P. So this P basically captures our degree of belief in the event A taking place, also known as uncertainty or confidence. It's a way of formalizing, when talking about uncertainty before, formalizing this idea. Let's look at another fun game. We have two notes, 2 unit wagers. Note 1 is outcome is heads. Note 2 outcome is tails. You decide P for note 1 and Q for note 2, and I decide whether to buy from you or sell to you each one of the notes at the price that you set, price that you determined. Now, if you choose P plus Q to be smaller than 1, then obviously I would just buy both of these notes from you, because I'm guaranteed to make money. So if you choose P plus Q to be smaller than 1, I will buy from you note 1 for P and also note 2 for Q, because whatever outcome it is going to happen, then you lose money. I gave you P plus Q, which is smaller than 1, and you always guaranteed to give me 1. So you lost 1 minus P minus Q. So this is actually an example of something called a Dutch book, which is a set of wagers where you decide the odds, wager price, and I decide whether to buy or sell each note, and you are guaranteed to always lose money. You can play that at home. Set of beliefs, it's called rational, if no Dutch book exists for that set of beliefs. So we can actually formalize rational beliefs in a very interesting way. We're going to define sample space X to be a space of simple events, like possible outcomes from experiments, like flipping coins would be heads, 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 tails, tails, heads, tails, tails. We're going to define A to be some event, subset of A, subset of X. A holding true means that at least one of the outcomes in A happened. For example, at least one heads from 2 tosses. A would be heads, 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 tails, tails, heads. We're going to write PA for the belief, for your belief on event A. Your wager on A happening, assuming that all wagers are unit wagers. We can show, turns out that we can show that the set PA for all subsets A and X are rational beliefs if and only if that set PA satisfies the laws of probability theory. We already showed that PA plus P of note A, complement of A, equals 1. You can try to devise other betting games at home to prove the other axioms of probability theory, or you can just go on bdl101.ml/betting to see how to prove the other properties. That basically means that we can derive the laws of probability theory from rational beliefs. Or, equivalently, that if you want to be rational, you must follow the laws of probability theory. Otherwise, someone can take advantage of your machine learning model. Above is known as the Bayesian probability theory. It forms an interpretation of the laws of probability and formalizes our notion of uncertainty in events. You can contrast that to frequency-as probabilities, which is only applicable to repeatable events. Like frequency-as probability is the stuff that you usually get taught in school, which is how many times you flip the coin, you get heads, you look at the ratio of that as your number of times goes to infinity. Frequency of that is going to be the probability. That's a frequentist interpretation of probability theory. You can't really use it for non-repeatable events, like what's your belief, what's the probability that Donald Trump will win the 2020 elections? Also some other issues which we're not going to talk about, and the issues of Bayesian arguments as well, which we're not going to have time to get into. I'm just going to give this one quote-unquote real-world example. Did the sun just explode? Next KCD comic. It's night, we're not sure. So you have two scientists that built is one of these? Yeah, okay. Two scientists building a neutrino detector to measure whether the sun has gone nova. It rolls two dice to see whether the sun has exploded. Then if both come 6, then it lies to us, otherwise it tells the truth. Run the experiment. Frequentist statistician sees the result of 1/36, which is smaller than 0.05, which is your confidence interval, therefore the sun has gone nova. The Bayesian statistician would bet the neutrino detector 50 quid that the sun has not gone nova. Which leads us to actually something more interesting, which is Bayesian probabilistic modeling, or using these ideas in machine learning, which is a simple idea. If you're doing, I don't know which one is on. There's definitely, okay, whatever. Core idea over here is that if you're doing something which doesn't follow from the laws of probability theory, then you're doing it wrong, basically. Let's start with a very simple observation that we can't do machine learning without making assumptions. So we must make some sort of assumptions about how our data was generated. There always exists some underlying process that generated our observations. In Bayesian probabilistic modeling, we make these assumptions about underlying process explicit. And we want to infer the underlying process, i.e. we want to find the distribution that generated our data. For example, in astrophysics, gravitational lensing, we know that there exists some physical process magnifying faraway galaxies. For example, could be that nature chose some lensing coefficients from some galaxy, which using some gravitational lensing mechanism transforms the faraway galaxy and gives us the observed galaxy that we have. We only observe the transformed galaxy, and we want to infer the lensing coefficient. Another example is classifying cats and dogs. There exists some underlying rules which we don't know. For example, if the thing in the picture has pointy ears, then it must be a cat. We observe pairs of images and cat, not cat labels, and we want to infer the underlying mapping from images to labels. Or in Gaussian density estimation, which is a toy example that we will use for the next few slides. I actually tell you the process that I used to generate some scalars. I give you 5 data points sampled from some normal distribution with mean, mu, and variance sigma squared. In this case, we're going to assume sigma is going to be 1 for simplicity. You observe the points x1 to x5, and you want to infer my mu. Just as a reminder, this is what a Gaussian density is, in case you don't remember what Gaussians look like. So I give you some data points. We don't really care about what mu generated the data. We care about what's the probability, for example, that mu equals 10 generated by data. We want to infer distribution over mu. Let's look at some different hypotheses, different models that could generate the data. For example, a Gaussian with mean at -2 or -1 or 0 or 1 or 2. We can see over here the x-axis, like the probability, well, that's the input scalar and the probability that the Gaussian density, probability density that Gaussian would give to each input to the density function. Or you can see the same 5 Gaussians over here in hypothesis space, which is mu by sigma. All of these have sigma equals 1 and mu between -2 and 2. I chose one of these Gaussians. We make it very simple as a starting point example. And I generated my data from one of these Gaussians. In Bayesian modeling, we basically want to represent our beliefs or assumptions about the data, about how the data was generated explicitly. So for example, you can do that via a generative story, which is basically saying my assumptions are that someone, me or nature, or someone selected some parameters, mu star and sigma star, generated some n data points from that normal distribution with those mu star and sigma star, gave us that data set x1 to xn, and we would now want to formalize this process. We're going to do that using a probabilistic model. We're going to define some prior of what I believe the parameters might look like. Example, I think that mu could be somewhere between between -100 and 100, or could be any real number, very wide dispersed distribution. We're going to define a likelihood. How do I believe the data was generated given the parameters? So if you give me some mu and sigma, I think that xn just follows a normal distribution with mu and sigma squared, which is literally the model that I told you about how I generated the data. We will update our belief on mu, condition on the data you give me, in order to try to infer the distribution over mu. We're going to try to find the conditional probability of mu, condition x1 and up to xn. How are we going to infer mu? For that, we need the laws of probability. Actually, everything that we're going to talk about follows the laws of probability. We're going to use this simple sum rule, which is just p of x is the sum of p of x and any joint y, or you can think about that as integrals integrating over y. We're going to use the product rule. Any joint p of x and y is just p of x conditional y times p of y, and base rule. P of x conditional y is just p of y conditional x times p of x divided by p of y. H is often, on the right-hand side, H is often omitted to keep stuff clear and clean. Can you find my Gaussian? So remember that products, ratios, marginals, conditionals, lots of other stuff of Gaussians are Gaussian. And you can actually find a summary and playgrounds for all of these things if you go on bdl101.ml/Gauss, summarizing all of these different properties that we're going to use. We're not even going to use any of these equations. It's just to convince you that all these Gaussians are very well behaved. The main thing that we're going to use is actually this equation. And that's the main equation that we're going to have for the rest of the that's the main equation we're going to have for the rest of the talk and different variations of this equation. So that's base rule, probability of x condition y. And in probabilistic modeling, we're going to replace x with mu, parameters, replace y with d, the data, and h is going to be our sigma and h. Basically, what we have is probability of mu conditional d equals probability of d conditional mu times p of mu divided by p of d. The left-hand side is called the posterior distribution. Right-hand side is composed of a product of the likelihood, the prior distribution, normalized by the model evidence, which doesn't depend on mu. This is constant with respect to mu. Model evidence by itself can be just evaluated using, again, the sum rule, the summing over all possible mu values for mu. We're going to try to understand each one of these terms in a bit more detail. We're going to talk about the likelihood. After that, we're going to talk about the posterior in more depth. We're going to try to get an intuition into what these things look like. So the likelihood, again, we explicitly assumed that our data comes from IAD, from a Gaussian distribution. So we're going to compute P of D conditional mu by just multiplying all these P of xn conditional mu. That's just the product rule that we had before. The probability of observing data points, that basically captures probability of observing data points for a given set of parameters. What does it look like? For this hypothesis, m equals -2, and some data points, it's basically going to be, you're going to just draw some straight lines going from the data to the density. You're going to get a bunch of densities for each one of these. Let's look at a single data point. Single data point going through each one of these hypotheses is going to give us different probabilities, different PDFs, the densities actually, for each one of these points. So for this hypothesis, the probability that we generated x, single data point x at naught gives us a density of 0.05 or 0.24 for this hypothesis, or 0.39 for this hypothesis, and so on and so on. You can actually plot all of these in a hypothesis space. So over here we have mu by sigma by the density. For sigma equals 1, you can see that each one of the hypotheses has a different probability, different density for that single data point. If we actually look at a smaller sigma, you're actually going to see some very weird behavior. We're going to see that if you were to try to maximize the likelihood, basically trying to find the mu that will give you the highest maximum likelihood, the highest possible likelihood of observing the data, then you would find that at mu equals 0 and sigma equals 0, you're going to get basically infinite likelihood. I don't think that makes too much sense because I told you that xn comes from a normal distribution. I even told you that sigma equals 1. So it's actually a nice example of MLE, maximum likelihood estimate failure, and I'll come back to that later. Let's go back to multiple data points. So we have some multiple data points. We look at the density for each one of these. Remember, our likelihood is just the product of the density for each individual data point. We're just going to multiply all of these, which gives us this probability for each one of the hypotheses. That basically gives us a very nice intuition what the likelihood actually does. The likelihood function shows us how well every function value mu and sigma predicted what would happen, predicted the data that we actually observed. If we go back to Bayes' law, Bayes' rule, you can look at the posterior in more detail. The posterior, in contrast to the likelihood, would say, with the data that you gave me, this is what I currently think mu could be. And I might become more certain if you give me more data. And as a side note, the normalizer is the marginal, also called the marginal, the model evidence or marginal likelihood. It's just the sum of the likelihood times prior. It's often difficult to calculate. I'm going to talk about it much more in the next lecture. Can do an actual example of inference over here. If you give me a prior that we believe the data is equally likely to have come from each one of these 5 hypotheses, i.e. we say probability of mu, taking each one of these mu I, mu 1 up to 5 is just 1 over 5, then the marginal likelihood is just going to be the sum of the likelihood times the prior, which is just 1 over 5 times likelihood for each one of these mu's. The posterior is just going to be 1 over 5 probability of that mu divided by this quantity, and that quantity just comes from what we did over here. The marginal likelihood of sigma equals 1 is basically P of D condition sigma equals 1 is the probability that data came from a single Gaussian with parameter sigma equals 1. Marginal likelihood of the hypothesis, P of D condition H, is the probability that data came from a single Gaussian with some mu and sigma. Any questions so far? We're going to have much more technical stuff soon. So we're going to talk about probabilistic modeling of functions. Okay, yeah. Yeah, okay. So we're going to talk about modeling of functions. We're going to look at some examples going beyond just simple beliefs over statements like heads happened, or we have some, like looking at probability of scalars mu taking some value. So this is an example that we started from. We have some distribution over functions, f1 and f2. We would want to know uncertainty or belief in these systems, in the predictions from this system. We want to know the distribution over the outputs for each input x, or we basically want to find the distribution of the functions. So before that, we need to go over some preliminaries. We're going to go over some history and some notation. So we're going to start with linear regression. I hope everyone likes linear regression, due to Gauss, 1809. If you give me a set of n input-output pairs, x1, y1, x2, y2, up to xn, yn, for example, this could be the average number of accidents for different driving speeds. We're going to assume that there exists some linear function mapping from these vectors xi, which are in some RQ space, to yi, which are in some RD space, yi potentially co-opted with some observation noise. Our model is a linear transformation of the input. So f of x equals wx plus p, where w is some d by q matrix for the real numbers, b is some vector of d elements, and different parameters w and b define different linear transformations. Our aim is to find parameters w and b that minimize, for example, the sum of the square differences between yi and wxi plus b. But the relation between x and y doesn't actually need to be linear. We can look at linear basis function regression due to Gerjun, 1815, Smith, 1918, going 100 years back, more than 100 years back, where input x is actually fed through k fixed scalar valued nonlinear transformations, phi k of some x, and then we collect these k nonlinear transformations into a feature vector. So we have phi of x is just phi 1 of x, phi 1 of x, phi 2 of x up to phi k of x, and then we just do linear regression with those phi x vectors instead of x itself. So this, with a scalar input x, the transformations could be wavelets, for example, where we take the wavelet number k is going to be cosine of pi kx times exponent of minus x squared. These could be polynomials of degree k, x to the power of k for each element k. So phi k is going to, phi of x is going to be x, but it's going to be constant, 1 plus x squared. Well, phi x is going to be 1x, x squared, x cubed, and so on. This could be sinusoids with different frequencies, sine kx, for example. When phi k just equals the kth element in x, then basis function regression just collapses to normal linear regression. The basis functions are often assumed to be fixed and orthogonal to each other, and we often look for an optimal combination of these. That might sound familiar if you've done linear regression in your undergrad, for example. That's not what we care about. These don't really need to be mutually orthogonal and fixed, which can basically lead us to parametrized basis function. So parametrized basis functions, I couldn't find a single citation for that, but you can look at Bishop 2006 and many, many others. For example, phi k parameterized by some wk bk, where the scalar valued phi function is applied to the inner product w transposed x plus p. Phi is often defined to be identical for all k, so only the parameters wk bk change. For example, phi k could just be the tan h function, giving phi k wk bk x is just tan h of w transpose x plus p. So some notation and terminology, pay attention. Feature vector, or basis function outputs, is the input to the linear transformation over here. And in vector form, W1 is a matrix of some dimensions q by k, which maps x to some feature vector. B1 is a vector of k dimensions. Phi of W1, B1 is just phi of W transpose, well, W times x. B, W2 is a matrix of dimensions k by d. W2 mapping from k by d feature vector to output y. B2 is a vector of d elements. Model output is going to be phi of WB x W2 plus B. And we want to find some W1, B1, W2, B2 that will minimize, for example, the sum of the square differences between our observed yi's and the function outputs over the input xi. Everyone is happy with that? Anyone has any questions about this stuff? It's good. So I have a specific notation over here, like what k is, q, d, and so on. If you do get confused, if you go on bdl101.ml, then there's a summary of all this notation, so you can just keep it open if you want. Okay, that leads us very neatly to hierarchies of parametrized basis functions. Due to Rumelhart and others, 1985. These are also called neural networks for historical reasons. These have multiple layers, which are the feature vectors we talked about before in the hierarchy. Each linear transformation is also called an inner product layer or fully connected layer. The transformation matrix that we talked about is also called weight matrix W. The intercept is also called the bias B. Units are elements in a layer. So this is the, we have, input layer. We have an input layer, which is basically the X itself. It's a bit confusing. Output layer, which is model prediction. The hidden layer, first hidden layer, second hidden layer. So this is a 2 hidden layer neural network. Units are the elements in each layer. Elements in the feature vector. We have 4 units over here, 4 units over here. Feature vector is a very overloaded term. It often refers to the penultimate layer, i.e. at the top of the model, just before the softmax, or just the last linear transformation. So this is the output, this is the second, this is a feature vector over here. We're going to denote a feature vector phi of x, like what we had before. So phi of x is going to be a feature vector that has k units or k neurons, which we're just going to call each one of these phi 1 of x up to phi k of x, k by 1 vector. So we're going to look at all the stuff before that as just some deterministic finite transformation. We're going to denote the feature matrix phi, capital Phi of x, to just be the collection of all these feature vectors over all data points x1 up to xn, an n by k matrix. We have n data points, k dimensional feature vectors, that's going to give us an n by k matrix, phi x. Regression is often done when we compose multiple basis function layers into a regression model, and the last transformation, also called the model output, which is this one, we often don't apply nonlinearity over here. We want that to be close to the scalar output you give me. Classification, we further compose a softmax function at the end called logistic for 2 classes. This is what it looks like. For large O value over here, it's going to be near 1. Small value, it's going to be near 0 over here. It should go at 0, it should be at 0.5, 0.5. This is my bad drawing. It squashes its input into a probability vector, i.e. a vector whose elements sum to 1. If you do classification, that will basically be the model output, or the softmax vector, or the softmax layer. The stuff that goes into that is often called the logit vector. which is the feature vector we talked about before. So these things basically define building blocks, where we can, each layer is very, very simple. We can compose them in modular ways to get very complex and versatile models. And many, many, many engineering efforts have gone into building very good tools that scale very well and work very well, lots of really nice, interesting applications. For the moment, we're going to make some simplifying assumptions. We'll use deep neural networks and denote by W the weight matrix of the last layer, and by B the bias of the last layer. We will assume that everything else is fixed. We're going to only look at W of the last layer. All the weight matrices other than W do not change. And we're going to go back to that later, actually tomorrow, and see exactly how we can remove that simplifying assumption. But that's going to make it much, much simpler to explain a lot of the actual underlying concepts over here without having to talk about all the actual details which are not that important for the intuition behind stuff. So we have a linear transformation from the feature vector to the output, which is parameterized by W. That's going to be the only thing we care about. Everything else is fixed. We assume that Y is scalar. Again, simplifying some stuff. So W is a k by 1 matrix. We're going to write WK to be the kth element of that matrix. We're going to assume that the output layers B is 0, which is the same as assuming that observation Ys are normalized. Again, these two assumptions simplify the derivations, but there's no difference whatsoever if you remove these assumptions. Everything is exactly the same. So our function output fw of x is just going to be the sum of wk times phi k of x, or w transpose phi x, where phi x is our frozen feature vector for some neural network. It's funny how everyone woke up when I started talking about neural networks. Some notation we're going to talk about, you have to remember. X is our input matrix, an n by q matrix. Lowercase x is an input vector, q by 1 vector. N is the number of data points. Xn is going to be the index over the data points, lowercase n. Q is the input dimensionality. D is the output dimensionality. K is the number of units in our feature vector. D is a collection of data points that you observe, x1, y1 to x and yn, which is just going to write as xy, two matrices of n by q and n by 1. We assume number of output dimensions D is 1. Okay. So remember that we want to put a distribution over functions. All of this was just set up so we can put a distribution over functions. We need to define a generative story. It's difficult to put distributions over functions, but it's much easier to put the distribution over the neural network parameters. So for the moment, we assume that the data was generated from our fixed function. Well, we assume that someone chose some W, which we want to infer, and then use that same fixed phi that we're using anyways, in order to generate the data that they give us. That's our generative story. So the assumptions we make about the data: nature chose some W, which defines the function fw equals w transpose phi for some fixed universal phi. They generated function values over inputs x1 to xn. So they generated fn equals fw over xn. f1 equals f of x1. f2 equals f of x2. Then they corrupted these function values with some noise, also called observation noise. So they took each one of these f1 and added some epsilon1 sampled from some normal 0 sigma square. f2 added some epsilon2 sampled from normal 0 sigma square. So it's called additive Gaussian noise with some parameter sigma. Yeah? It's the same. For the moment, we assume it's the same because we're going to do inference only over W. And tomorrow, we're going to see how we can actually infer all the other weights in a very deep neural network. Actually, the ones that we talked about at the beginning, or the examples we talked about at the start. Yeah. We are given observations x1, y1, x2, y2, and so on. And for simplicity, again, we're told that sigma equals 1, just because I want to keep stuff very, very simple for today. Tomorrow is going to be much more complicated. Okay, we have some questions we want to answer. So how can we find the function values f star for some new point x star? Or how can we find our confidence in this prediction? So remember that everything follows from the laws of probability theory. So we build a model, we put some prior distribution over W. P of W, we're going to say is just going to be normal 0, 1, or the equivalent for that in matrix case, in the vector case. It's going to be mean is 0, vector of zeros, and the covariance is going to be S squared, some parameter S times the identity matrix of dimension K. The likelihood, condition on some W, we generate observations by adding Gaussian noise. So the likelihood probability of Y condition on some W in X is just going to be a normal distribution with mean W transpose phi and some variance sigma squared. Is that clear? Everyone is happy with that? I mean, that just follows from our assumptions about how the data was generated. Yeah? Our prior belief over here basically says that WK is more likely to be in interval -1 to 1 than in the interval 100 to 200, which also means that the function values are more likely to be smooth than very, very erratic. Smooth than very, very erratic. You're going to see later why. What does that, like, how is that assumption mapped to that? Actually, that's very much related to stuff that Arthur talked about in the morning. I'm not going to go into detail into that, but there's a lot of literature on that if you want to read more. We want to infer W. So we want to find the distribution of a W given some data set that you give me, that I give you. So we can actually do analytic inference. We can find the exact posterior of a W because everything is Gaussian in this case. Stuff that is not Gaussian is fixed, so we don't need to worry about it. So P of W conditioned on some data X and Y. By Bayes' law, by Bayes' rule, it's just P of Y conditioned on X and W times P of W conditioned on X times P of Y conditioned on X. Everyone is happy with that? Now P of W conditioned on X is just P of W because we assume that W just doesn't depend on anything. We just assume W is normal 0, 1. So we just swap that over here. We can expand P of Y condition, actually no, P of Y condition X doesn't depend on W either. So if we keep only the terms that depend on W, then this is proportional to P of Y condition X and W times P of W. Everyone is happy with that? All the stuff depends on W is over here. And then we can just write that down explicitly. So again, our generative model, generative story, basically said that P of Y condition X and W is just the product of the data points of a normal distribution of drawing each one of these YNs from a normal distribution of mean W transpose phi xn variance sigma squared, and P of W, our assumption was just P of W 0 S squared. Yeah, so just plugging in the stuff that we had in the in the model over here. P of W is that. Likelihood, P of Y, condition some W, some X is that. And we just plug that into the equation over here. Yeah? Which is what?
Is there notation of K, it's the number of neurons in the last line?
Yeah.
So then, because, okay, in this slide, your prior doesn't depend on the K.
Oh, I just didn't write K over here. So that's still 0, a vector of K zeros and an array of dimensionality K. And yeah, I'm trying to keep the derivation as simple as possible, so I might remove some stuff just to make it a bit less cluttered. We can basically if you remember the definition of a Gaussian, and if you don't go on the supplementary material I have online, then we can just basically plug in the density for each one of these Gaussians. We're going to ignore the normalizing constant for the moment. So we're going to say normal Yn with mean W transpose phi, variance sigma, just exponent of minus half sigma minus 2 Yn minus W phi xn squared times some constant Cn. We don't care really about that constant because it doesn't depend on W. We're going to keep only the stuff that depends on W throughout the derivation. So we have times product for that over n. We have a product over here with exponent of minus W transpose W. Again, we're going to ignore all the stuff that doesn't depend on W. What we're going to get is exponent of minus half the sum over n sigma minus 2 of Yn minus W transpose phi xn squared, just like pulling all of the exponents together, plus S minus 2 W transpose W. And the W terms can be collected together. So we have some, we're going to expand that. We can ignore that thing which doesn't depend on W. So we're just going to have that term over here. And then we have all of these W transpose phi, phi transpose W, which is this stuff over here. Then we have this term over here. Now, you're going to just rewrite that slightly because remember that W transpose phi is a scalar. So we can just write it, like move it to the other side. So it's going to be, we can move it over here. That's going to be W transpose phi, phi transpose W. W transpose phi, phi transpose W. So these are the three terms that basically depend on W. And if you don't believe me, you can just, again, these slides are online, so you can go over the derivation a bit slower and may convince yourselves that that's fine. We're going to pull all the W's outside for the quadratic terms. We're going to get W transposed times the sum over phi times W over here plus that S inverse S to the minus 2i minus, well, 2 times this stuff over here. So this thing is that first term over here. Now, this is a nice technique, actually. We know that the posterior of a W, P of W conditional D, is a Gaussian distribution because properties of Gaussians, products of Gaussians, brushes of Gaussians, and so on, all of these are going to preserve the form. All of these are going to be Gaussian. So we can just write P of W condition D equals some normal distribution with some mu dash, some sigma dash. And we can actually just do the expansion inside the kernel, inside the exponent of those mu and sigma. It's going to be W minus mu dash, sigma dash inverse. The transpose over here, W minus mu. It's going to be W transpose, sigma inverse, W, minus 2W transpose, sigma inverse mu, plus some stuff that doesn't depend on W. And then we can just match the terms. We have W, basically we know that this must be equal to this stuff over here. So W transpose W basically means that this stuff must be equal to sigma inverse, to the covariance of this posterior. And minus 2W transposed must be equal to sigma inverse mu. So this stuff must be equal to sigma inverse mu. So we can basically just write it down as sigma equals the inverse of that, which is what I have over here, inverse of that. Or you can just write it down a bit prettier in vector form as sigma inverse times phi transpose phi plus S inverse to minus 2, all that inverse. And the posterior mean, which is just sigma times sigma to the minus 2 times the sum, or in vector form, phi transpose y. That's all. So if you know linear regression, this is just normal stuff you have in linear regression, but instead of having x transpose x and x transpose y, we have phi of x transpose phi of x transpose y. How do we do predictions with this model? Again, we're going to use probability theory to perform model predictions. What is the quantity that you care about when you do a prediction? You care about P of y star, condition x star, and some data. this is very simple. Like we're just gonna use the sum rule to introduce W. It's gonna be P of Y star and W, condition on blah, 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 integrating of all of W. Then we're gonna use the product rule to find P of Y star condition X star in W times P of W condition on X and Y. And X star, but it doesn't depend on X star because we don't have a Y star. So that's just applying the normal laws of probability theory. And then by model assumptions, if you give me X star and W, that's all I need to predict Y star. I don't actually care about X and Y anymore. That is basically what our model, generative story says and what the model says. How do we validate that? Again, we're going to go quickly over a new technique. Remember, the likelihood is Gaussian. We just found the posterior is Gaussian. So the predictive must be Gaussian as well. So we're going to actually use a different technique now, which is, I think, more fun. Again, we're going to write the predictive is just going to be normal with some mu star and sigma star. We know that the expectation of that normal is just mu star by definition of a Gaussian distribution. So the expectation of Y star with respect to this distribution should just give us the mean of the Gaussian. Now that expectation is just the integral of Y star times P of Y star condition X star in D. We're gonna do some shuffling. So we're gonna take P of Y star condition X star in D. We're gonna expand that using what we had over here. That's P of Y star condition X star in D. It's just the integral of Y star condition X star in W times the posterior. So we're just going to expand that, plug that here. We just basically plugged in the integral of the likelihood times the posterior, integrating over W. And then we have Y star over here. And we're going to do some shuffling around. We're going to move Y star in here. We're going to move dy star in here. We're going to pull the posterior and dw outside. You get this? Just after the shuffling. Now, this is actually very nice, because what we have here is just the integral of Y star times the likelihood, which is just the expectation of Y star under the likelihood, which by definition is just W transposed phi of X star. And that thing, phi of X star, doesn't depend on W, so we can pull that out. So what we get is the integral of W transposed P of W over the posterior, dW times phi of X star. And that thing, again, the first thing is the expectation over W with respect to the posterior distribution, which is just mu star, well, mu dash that we had before. So we can just swap that in as the posterior mean transpose times phi of X star. You can do the predictive variance at home. It's not that difficult. Oh, okay, yeah, you're actually a bit ahead of time. Okay. Do you have any questions about this stuff? Okay. Yeah? So that's going to be the entire topic of the discussion tomorrow. So tomorrow we're basically going to, well, actually that's going to be a good segue. So actually, okay, let's go over that quickly about what you should be able to do now. And then we're going to go back to this question in a second. So what you should be able to do now, you should be able to do density estimation of scalars. You should know when maximum likelihood fails and why. You should be able to use Bayes' law to make more informed decisions in your life, and win against finance in a series of bets. You should be able to argue with frequentists about the interpretation of laws of probability and argue with philosophers about the nature of subjective beliefs, and also use Bayesian probability theory in machine learning and perform predictions in machine learning correctly. Tomorrow, answering your question, we will see how we can decompose uncertainty into epistemic and aleatory components, and use uncertainty in regression correctly, and in classification as well. We will develop tools to scale these ideas to large, deep models, going beyond just the last layer. So we see how we can actually do inference over all the layers in the model, using approximate inference techniques, and then stochastic approximate inference. We're going to talk about stochastic variational inference. And then we're actually going to see examples of how to develop big deep learning models that can convey uncertainty with actual real-world examples in some interesting computer vision tasks, including active learning and autonomous driving, including the stuff that we have over here. Very quickly, though, stuff over here. Yeah, so just as a last slide, all the resources we talked about, including these slides, are available online over here. If you have any questions, I'll be here. And if you want to go over the derivations, so it's like at your own pace, then you're welcome to do that. I think tomorrow we're going to have even more derivations than today. So it will be good to actually understand the stuff we talked about today. And we have some more demos and some other stuff. Cool. Thank you. If there are any other questions, yeah.
In your example, what's the prior distribution, which was just a diagonal?
Yeah, so in the example that we're talking about, we just had a diagonal. It's even worse than diagonal. We just had a isotropic. So it's the same scale for each direction, for each axis, basically, which means that it is very limited. Basically saying that it is as smooth in that direction as it is in this direction. Yeah, it's very easy to change that to other pairs. In the derivation we talked about over here, it's trivial. In the stuff we're going to talk about tomorrow, it's going to be even easier, surprisingly, because what you're going to see tomorrow is that is just equivalent to L2 penalty, or L2 regularization over your weight matrix. So having different scales for different directions actually corresponds to having different L2 penalty, different L2 regularization over different columns in your weight matrix, which people actually don't bother doing. So that's interesting. Maybe we should play with that. Any other questions? Yeah? It might be easier if you use a mic, actually. It's difficult to hear you. Can you speak a bit louder?
Yeah. So we calculated the distribution of the weight.
Mm-hmm.
And can we effectively, so to calculate the distribution for the first layer and for the second?
So people are very impatient. Everyone wants to do do inference over deep models. You can. But it's not ready to do inference. It's, okay, one way of looking at things is you can think of phi as actually parametrized by the weight matrices of the previous layers. And what you can do is actually find the P of, do you remember we talked about model evidence, or P of probability of the data, integrating over all model parameters? What we can do is basically find probability of the data as a function of all the previous layers. And then you can do maximum likelihood over that by just, maximum marginal likelihood in this case. Trying to find the model evidence highest possible by just basically playing, changing this phi to be as good as possible. This can lead to a whole bunch of very interesting failures, which I'm not going to actually have time to talk about tomorrow, but other thing that we often do is we just do inference over these things. We try to find the posterior or approximate posterior for each single layer in your deep neural network. Now, none of these tools will work for the stuff we're going to do tomorrow. Stuff we're going to do tomorrow is we're going to use stochastic estimators, and we're going to use stochastic variational. First of all, we're going to talk about variational inference, which is how do we actually find approximate posteriors when we can do analytic inference. We're going to talk about stochastic approximate inference, basically how to use stochastic estimators like the reparametrization trick, or there's a bunch of other names for that in statistics literature. That's the one that we will look at least. And then we're going to see how that basically corresponds to like inference in very, very large models, including the example that we started from at the beginning of the talk with the dropout example. There is huge amount of literature that actually I'm not going to even be able to cover in the talk tomorrow. I'm happy. I'll add another page. Well, I'll add another resource to the website, to the resources that I showed, giving some more related literature if you want to read more about these sort of topics. I collected a long list of things to read about, including some books like Kevin Murphy's Probabilistic Machine Learning, and David Mackay's Information Theory, and Chris Bishop's Pattern Recognition and Probabilistic Machine Learning, and a bunch of papers. So I'll put all of that online. I think a lot of the stuff that you're asking about will be answered tomorrow. Any other questions about the stuff from today? Okay, thank you.